Good morning, everybody. Oh, we've got a little bit of camera blur there. Let's see if we can get the focus back. There we are. Good to see you both this morning. Good morning, Lily. Good morning. I think it said Blatz, is it? I'm not sure if I've got the pronunciation right there. I don't know if it's very easy for you to correct me over chat, but if I'm not pronouncing your name right, then I'm sorry, and I can try and do better if you give me a hint on how to. Yeah, I hope everyone's well, whether you're live with me now or whether close. Okay. Yeah, I hope everyone's well, whether you're live now or whether you'll be watching it later on catch up. We're going to continue diving into PyO3's procedural macros today. I don't think I've got any other announcements to talk about, so we might as well jump straight in to what we were going to look at. So maybe before we go look at code, we spoke a little bit on previous streams, and also I started a blog this week and I wrote a bit about PyO3's 0.21 bound API. And what we're going to do in 0.21 is we're going to introduce this new API, but, oh, good morning, David, as well. But we're not going to remove any of the existing API as much as we can. But what we do want to do is deprecate as much of the existing API as possible. And so if I just jump over to VS Code here, then let's see what we've got in. If we go here, oh, we've got a lot of stuff that I think, oh no, sorry. I want to look at this one. This is probably some stuff that we were looking at, something that I was doing middle of the week. Let's just go back to something that looks like this here. So, okay, we can remove a lot of these imports. Okay, great. So here we've got in our little example of some PyO3 code, a function that is just taking any Python object and attempting to call len on it. So this is very similar to the Python operation len obj, right? And we can show that if we just go in a terminal and demonstrate this quickly. Oh, we need the virtual environment activated. There we are. We can use Maturin to compile it, as we've been doing before on these streams. So we can and there's no real surprises here. So if we do like len of some number, then obviously that's not going to work. And our new function that we've written works the same way. And we could do it on a list, no surprises here. And we get 3 because that's the number of elements in the list. And the point is that what we're going to look into today is that here we've got in the function argument this GIL Ref or GIL Ref. I still haven't got the pronunciation of GIL decided on. David's asked about the stream or the PR we did to C Python last week. I'll talk about that in a minute. I'll just introduce maybe this a little bit further first. And so we've got this GIL Ref here, the reference to pyany, and the goal is we want to replace this like this with these bound references instead, which gives ownership. But you can take it as an owned reference like this, or you can take it as a shared reference. And the purpose being that this moves the control into user code, adds a little bit of complexity, but you overall end up with being able to get more performance out and better memory performance as well. So it's very worth doing. And we'd like it so that in PyO3 0.21, if people have got code like this sitting about, that we emit a deprecation warning for this, instructing them to change it into the bound form instead. So the trick is that this is not so easy to do deprecations in procedural macros. We can talk about that in a bit of detail. We'll go look at how the code works. Just before we do that, so David, the PR2C Python repo we did last week. So maybe we can jump over there in the browser. It was, oh no, it wasn't this one. That was the precursor. It was This one. So this is what we did last week, just as a bit of a summary. We went through introducing 2 new APIs to CPython, which we wanted to use for PyO3's sake to basically safely access the inner fields or the encoded data of PyUnicode type, PyUnicode being the C API name for a Python string. And quite fairly, I did warn everybody that there was going to be potential reasons not to do this. And Peter indeed commented back to advise that really the goal is not to do this in the CPython side, because I don't know what we're scanning exactly, but the main objection that I can gather is basically the problem that it relies on talking about the encoding, and the CPython developers don't really want to have to expose the internal encoding of a string object in this way. And so that's totally understandable. And so I think what we're going to do is that I'm going to have a little bit more of a catch up with Peter over email exchanges and maybe a private video call, just to like hash some details out of what we might try and do instead. And then I think what would be really cool is we'd quite like to think about maybe having a stream where we talk about what we might do in public instead, once we've got just a little idea of what we might talk about. So hopefully, maybe, I don't know whether it'll be next week or in a few weeks' time, but it'd be quite nice if we can do a follow-up where it looks like our original PR that we did last week is not going to make it across the line, but maybe instead we can all participate in a bit of a design discussion and figure out what we can do instead. So that's what we did last week. Right. And so, so got stuck for the moment in PR review, but we'll have some progress with that in the future, hopefully. And instead, this week, we're going to look at getting this deprecation warning added to this use of the deprecated GIL Ref type, so that we can instead encourage people to use bound types instead, like this. So let's talk about how this is going to work. But let's go back to, we've used cargo expand before. So let's just do that again. For those who didn't see the previous streams, cargo expand is a command line tool you can use to get the procedural macros to expand into a new Rust source file, so that you can see, oh, that's a warning in PyO3, which we don't need to worry about for now. So we get this new Rust source file, libexpanded. And in there, it's replaced these original procedural macro calls with the expanded result of them, which is quite a lot lengthier. There's a good reason why we have procedural macros to avoid all this boilerplate. And we can do quite smart tricks with the procedural macros as well, because we get the chance to omit all of this stuff. And let's just try and line these up for a second. So I'll move this one over to the right. It's going to be a little cramped on the screen just while we work out where we are, and then I will probably expand over the procedural macro code a bit more detail. So we're looking at this function object length. Can we see it in the right? It is, oh, it's up here at the top. Yeah, so that's lined up. And then this stuff underneath is the emitted macro code for this pyfunction procedural macro. And so there's some helper definitions, and then we wrap some stuff in a constant where we do, welcome, Peter. So yeah, we were just talking a little bit about the CPython PR and how we'll be maybe reviewing that in the future together. But yeah, okay, so let's go look. This is all the code that we emit, and in particular, the piece I'm looking for. Oh yeah, so this is the definition we've talked about a little bit before with, I'll make this bigger. Let's move this back over onto the left-hand group. So this bit is the function we wrote. This is the pyfunction output underneath. This is the bit which is creating a pymethods. It's actually a safe wrapper around CPython's pymethods, but this is defining how we're going to expose this to the Python interpreter. We don't need to talk about that here. And then this bit underneath is creating a hidden function, which we're using in PyO3 to wrap this original one. And it's kind of like the plumbing between what you've written here and what CPython wants you to have. So in this hidden function, well, we call it from the definition that we're giving CPython up here. This is where we're referencing this one thing, and it only gets referenced in this one place. And in this hidden function, we take, first off, we take the proof that we've got the global interpreter lock, or access to Python interpreter. And then we take all of the other stuff directly from CPython. So self will be in the type of a pyfunction. It's probably not meaningful unless you want to know the module. We looked a little bit at pyfunction pass module in a previous stream. And then it takes the arguments, and the keyword arguments are also in this array, actually. It's a const pointer to a mutable Python object. So it's a pointer to a pointer, and then it's also got a number of these pointers. So this is like combined. It's a Rust slice, you could think of it as. There's a pointer and a length here. And then finally, there's also keywords names are passed as a tuple so that you know what keywords are contained within this array as well. I don't really want to talk about that particular mechanism right now. But then what PyO3 does is it goes from these raw values. It has a definition of what we're expecting to take. So we call the function object name. It takes one parameter called object, or obj. We wrote up there. It is, oh yes, it is a positional only parameter. I was surprised to see that. That's because we put a signature on here, which was requiring object to be positional only. You don't have to have this bit. This was just left over from some previous code that I was writing. But so PyO3 knows that this is expected to be a positional only parameter. So it's saying that there's only one, and it's required. And then we have this line is not expanded well, but we try and get all of the arguments out of these three fields. If we look for args down below, we can see it gets passed in this crazy long line. I don't really want to read it, but it's calling into PyO3's internals here. And the result is that we end up with this output. Actually, we could annotate a type on it. It's I think it's this type at the moment. So it's an array of optional, because function arguments to Python can be defaulted. So we deal with that optionality here. And then it still uses PyO3's internal GIL Refs, but I've got a PR that's not quite merged yet to remove this over to the bound API as well. So that's how, in this machinery, PyO3 is basically checking that there's one object. The type we put is pyany. And so there's not any like type checking going on there at that point. It's just checking that there's one argument passed positionally. It's called object. We don't need that for the keyword argument's sake, but PyO3 can still emit error messages knowing that the argument was supposed to be called object. So that's what this step will be doing. So we can, to kind of demonstrate that maybe in a little bit more detail, if we're running, if we import this again, and then do with our function, if we pass it 2 arguments instead, for example, it's saying it takes 1 positional arguments but 2 were given. And so that is actually coming out of this line when PyO3's understanding what came in from CPython and then converting it back out into the Rust function call. And so similarly, if you pass none, then we say we're missing 1 required positional argument object. And so that's come from this information here in combination with what got sent in. And then I think the bit that we're trying to solve is this little bit later on. So we've got any type of argument here. And eventually, where are we looking? We should be, we call the function here. So there's a little bit of helper code here. I can't remember the full detail on why we had to do this. It was something about name conflicts, but we save the actual function called object_len. We just refer to it up here, and then we call it down here. and we call it with this construct, quite a messy beast, trying to convert whatever's in here, the first argument, into the first argument of the function call. And it's a required argument, so there's this bit of helper here to make it forced to be required. And then there's this code which deals with basically converting it from one type to another. And it's inside PyO3's implementation module. And the tricky bit here is that this is all like very, very generic code trying to deal with just converting any old type into the types which users have placed in the top here. So if we change this, for example, to be a bound type instead, like this, which is what we eventually want to get to, and then we run cargo expand one more time, then, I'm just going to need to reload that file. We see, there's not an easy way to see. Let's just call this object bound just to show you that differences have gone on. And then let's go one more time into this. So now you can see we've recompiled it. Re-expanded it. The parameter is now called object bound. We can see that that's going on in this machinery here. But otherwise, the machinery that's gone on here hasn't changed at all. So the procedural macro is completely unaware of the type that's going on here. We've literally just left it to Rust's trait system to figure out what the right conversion is. And that's generally a very good thing to do, because procedural macros only get to analyze the text form of what they get. Like, it doesn't need to know anything about bound or pyany. And, you could, as a user, do something like this. And then you could just happily use this type, and you'd expect it to work. And so the procedural macro would never know, because it's just got this source code to analyze when you put a macro annotation on that you did this type definition up here. So we can't actually rely on the fact of knowing anything about the names of the types based on what we see. It's just not an assumption that holds. So this challenge that we're facing of how to deprecate this form is entirely something that we're going to have to figure out using like Rust trait machinery and somehow change the way that this bit works to achieve that. And so I'm not entirely sure that we're going to succeed, but it would be very, very nice to succeed if we can. So that's like difficulty number one. We've got to somehow do this using Rust trait system. And I guess like related is that procedural macros don't have a good way to emit a deprecation warning anyway. So because procedural macros can only produce more code. And it might change in the future. There might be a way to emit deprecation warnings from procedural macros in a future procedural macro API for Rust. But at the moment, procedural macros just emit more code. And the only thing that they can really achieve in terms of heuristics is they can emit compile errors. So there's this compile error macro, which you can use to basically fail the compilation, the Rust compilation. If this is ever seen by the Rust compiler, we'll just fail to compile. And so PyO3 can use that. So for example, if we added a second argument that we were expecting here, we get an error shown. And this, I think we should be able to expand and see it. Let's see. Okay, no, it's the cargo expand hasn't liked it. But what's going on there when we're getting this error message, signature entry does not have a corresponding function argument. That's because we're trying to specify the Python signature here, and there's only one argument actually allowed by this function, but we wrote two in here. So the point I'm trying to make is that PyO3 has used that compile error macro, which we just showed, but we've lost over here. So PyO3 will have put something like, what is that error message? Yeah. Signature entry not have corresponding, so forth. I hope you get the point. So when PyO3 was processing this macro, it realized that it wasn't valid. It wrote something like this out as the result of the macro expansion. And that's how the compiler shows you the error messages that you can get from using PyO3's macros incorrectly. But again, that's not a deprecation warning. So that's, again, another reason why for this deprecation warning, we're going to have to try and do something smart with the traits in what we're achieving here. And so that's kind of bringing on to the next bit. Like, how are we going to achieve that? We need to somehow change this block of code so that it goes down a pathway which only emits an error or a deprecation warning if it's encountering one of these types that we don't want to see anymore. I'm just going to have a sip of coffee now while I think about this next bit. Yeah, okay. So I guess one more constraint related to everything that we've been looking at is that because we don't know compiler warning, David. Yeah, so there is a possibility to have something like compiler warning. I think there's design questions around it. I don't remember the full details right off the back of my mind, but there's some reason why the compiler team would like to do better. I think it's related to, like, you probably want to be able to silence warnings and things like that. So you kind of want them to be nameable. There's more complicated things around warnings. Whereas if it's an error, it's easy enough, like stop compilation, that's fine. You don't need to have kind of interactions of the user with the compiler warning or with the compiler error. But with a warning, there's more things that a user might want to do with it. So you need to give more control. And I think that it's waiting for a decision on how that might work is kind of where we're at. So maybe in the future, this all gets lots better. But even so, the point is that even if we could do that with the procedural macro, for some things it'd be very, very useful. For this particular case, it doesn't help us because we're kind of reliant on the type analysis, which we can't do because of the fact that people can put in the type aliases. Oh, we've lost that now. Never mind. It was like this, wasn't it? So if people did something like, we could do the same thing with this. It could be, we could have this type, right? And we still want the warning to be omitted there. And so that means that we can't just analyze the name by any and put out a warning. We have to somehow do it through the type system. Okay, so I think what I'm going to do is let's switch over to the browser, and in particular the Rust playground, to try and show I think this is going to look like. I think it will be easier to explain on a playground. So, maybe we can do that coloring instead, maybe, to match what we've been doing on the stream. Okay, so the idea here is that we want to be able to have a deprecation warning. So there is this attribute deprecated that we can put on functions. So if we write code like this and then call this later on, then the compiler will give us a warning that we're using a deprecated function here. And I think that we're going to somehow have to hook up like the Rust trait system to be able to emit the deprecation only when we're using a type that we don't want to. And this is, I think the trick that we're going to lean on is what we sometimes call deref specialization or autoderef specialization. There's different forms of it. But the idea is that this would only really work in sort of like macro output, stuff where you actually know all the types. You can't express this deref specialization that we'll talk about in generic code. And so to give you an idea of how this would work, let's write a struct A, which contains a struct B. And okay, so we have to define struct B like this. And then let's give A a method. Hopefully this kind of idea, there's lots of different forms of how this specialization can work. I think this is where we're going to have to head for our problem today. Let's give A this same function foo. And let's give B a function called foo as well. And so if we do this, where we create a new A, maybe it's a good idea to print some output here. And then we can do this. And I think it will be no surprise to everybody if we need to take our argument. Then, okay, but ignoring the warnings, then what we get as our final output is just this. We printed A because calling a.foo, no surprises, runs A's method. But if we now take this one out just for a moment and we try and do this, there's no method named foo, we can make B's methods available to a type A by implementing this trait called deref. We can talk about this in a little bit more detail. The deref type allows us to convert references of A into references of B through a dereference. So it's implemented like this. So that would be our implementation. And now that allows us to achieve this, where we had an A, and by taking a reference to it, we can allow dereferencing. This is a deref coercion even. We could be more deliberate about this. We could stick that on, but this will coerce just fine. Now we could write b.foo. Oh, the playground really wants to stick to the bottom. Let's just add some new lines in. So in this code, because we go through deref, now we're calling b.foo, so this will compile again. We can take this one out the top, get rid of that warning. And we see now that it's printing B. No surprise, we got rid of A's implementation. If we put A's implementation back in, we're still going to be calling B's because we converted explicitly to B. And if we put this one in, a.foo, this time we're calling A's implementation. So now we've got an A and a B. And this isn't yet using any of what we call this deref specialization. But what we want to do is we can actually limit when method resolution's running, which of these functions gets selected. And we can do that by, instead of having just A and B like this, we can actually limit this implementation to some types T. Let's just call the trait call A for a moment, and then we just have a trait call A, which doesn't need anything else. We're going to need to go one step further here. We need to somehow constrain this type T. And we'll do this by making A and B generic. There's different forms of this deref specialization. There's a really good article on it. I'll try and dig that out maybe in a moment. Let's just go with this for the moment. And so BT is going to need to contain T like this. And so, okay, so now everything's been wired up. Let's take this out again, just to reduce complexity. So we've just made the types generic for some type T. We haven't put any constraints on T at all. The only thing now is that we might need to stick in like the number 5, for example. So now we're making A and B generic, but we're forcing them to be integers here. Oh, I've missed the generics off this one. Now we can compile. Where are we missing? Oh, that's a generic type as well now. So I'm just going to leave a wildcard. We're back to the same situation we were before, where we're calling A and B separately, according to this conversion. And so let's now just remove that call. And we're interested in achieving a result where we can have a.foo either call A or B's implementation according to the type that we put into A. And that's where we can be a bit cheeky here. If we put a constraint on this, as I was beginning to show, call A, then it's going to mean that this A's foo is only available if the type T implements this trait to call A. And so what we should find, if we run this now, is that this is going to print B because we haven't implemented the trait for any types. I'm hoping that we get the result we expect. Yep, there we go. So we printed B. And so let's be a bit deliberate about these types. Let's call this 32-bit integer. And then let's repeat this trick with an unsigned integer, just for the sake of having two different types. We do this now. We're going to print B twice. But what we can do is we can implement this call A type for just signed integers. And now what we should find is that because we've added this trait implementation, this time when we call a.foo, this type T, being i32, required to implement call A, does implement call A. And so for the signed integer, we'll end up calling A's method. For the unsigned integer, we still haven't implemented call A, so we'll end up calling B's method. And we can begin to get the sort of effect we want. So if we run this now, you can see the output is first we call A's method with the signed integer, and the second time we've called B's method with the unsigned integer. The point here, and why this is kind of well suited for procedural macros and not well suited for normal generic code, is imagine you wanted to write some function, call foo for T, where you take a reference to A, T, and we call a.foo. Does anyone want to take a guess in the stream chat? If we call if we do call foo now instead of this in both places, what output do you think we might get? Stream chat. If we have, so we've changed our code. So when we had a.foo and like this, we got the output A here, and we got the output B here because of our trait implementation here, removing this method from the resolution for this type, for this call. So if we do this now instead, where we've wrapped it in a generic function T, any guesses as to what we might get from calling this twice? So there's possible combinations, right? Feel free to just place in chat. So we could have A, B, as we did before. We could get A, We could get B, B. Anyone in chat going to place a guess? Let's call these 1, 2, and 3. I imagine you're all thinking hard. Okay, we've got a vote for AB, which makes sense, right? It sounds like that would be based on what we saw before. So David's also gone AB. It's consistent with what we've written here, right? Okay, so it's 2 votes for option 1, but it's the same as before. Okay, I think it sounds like everyone else is thinking hard. So at this point, let's go and see what the output is. Let's run this. And the result is BB. And why? This looks surprising at first, but this is my point about why this kind of trickery we're doing only works in procedural macros. The problem is that in this function call foo we wrote the type T, generic T. We didn't say anything about call A here. And so that means, yeah, it's a hard one. I think everyone gets this surprised, and it's why this specialization technique isn't more common, because it's really only available inside of stuff where the types are really clearly written, which is normally just in like procedural macro output. Like you can get away with this in very select places in your code base, but for most code where you're trying to do like library stuff that's generic over types, this just doesn't work. The reason why is because we didn't have this bound here, right? So the compiler isn't allowed to reason about whether T implements call A or not. So yeah, exactly. And so because the compiler can't reason about the call A bound at all, this is completely ignored. And it can only go through the deref for B and then call B's foo. And so we could flip this around. We could add the call A requirement here. This time, we'll actually get a compile error first, because on this line 35, we don't have call A implemented for this one. So let's comment this out. And this time, this one, it's only this one call is allowed to compile, and it prints A. And that's because we've now forced the call A bound. So that means that every time this method's being evaluated, this time, it has to go through the A's foo, because the requirement call A is satisfied. And so being able to do things more generally, where you can get like this kind of effect, where you have multiple definitions of a function, is the more general form of specialization, and we don't have that in Rust yet. There's a lot of reasons why we would want it for efficiency, but it's got complexity that the language team has been working hard to solve for many years. So for the moment, let's bin that. The point is, in procedural macros, we can get away with writing code where we can rely on being able to avoid having to call other generic functions. And we can do some construct like this, where we can have the switch work between A and B. And even better, we can deprecate, I think, this is what I'm hoping works. We can deprecate just one of these two choices. And because the compiler can reason about the complete types, we can see we've got a deprecation warning for this one, but we haven't got the deprecation warning for this one. So this looks a lot like, I think, what we want to achieve in the procedural macro for PyO3. We want to get to a point where this aren't generic. Sorry, we've got a question from Blair. So aren't generics monomorphized? So my naive thought would be compiled with reason about each generic type in isolation. So Blair, that's exactly what. So that question is, oops, going back to this function, and oh, sorry, not this function, this form, and saying, isn't this substituted? So isn't the compiler thinking about this as two separate ones, if you like this? And the answer is sort of yes and no. In the type checking phase, when it's deciding how things are getting, like whether the types all line up, then it's reasoning about just a generic T. When the final code generation is happening, yes, the monomorphization happens, and we end up with basically these two functions. But the problem is because of that disconnect between type checking and monomorphization. And there's a lot of written detail about why specialization is hard. If type checking and monomorphization don't agree on what's happening, then we end up with unsoundness in the compile, which can lead to all sorts of nasty stuff. And so that's why specialization is not stable as a language feature, because there's a disconnect between how type checking wants to reason about this code and how monomorphization could reason about this code. And so the only way to make that sound is if monomorphization agrees with what type checking says, that always the call A bound's not available, basically. There's a bit more detail than that. I'm not really the one person to explain the machinery inside the compiler. I've got like a working knowledge of how it might behave, but ultimately the compiler experts are the ones who could describe that better than me. But yeah, so it's quite surprising that the call A bound is completely ignored. But once you're used to how Rust is reasoning, it's not that hard of a surprise. As far as type checking goes, there's no connection between this and call A. But at monomorphization, yeah, you might hope that it would, but it can't, is the point. Cool. So let's jump back. We got to our situation. You're welcome. I'm glad you're enjoying David and Blatz. Great. So we've got to this situation here now where we're able to make it so that we can deprecate just what some usages. Oops, I've got something wrong still. I've taken out our switch, the trait implementation. So we're getting one deprecation here, and this one is not deprecated. And so what I think we want to head towards is that we want to be able to adjust, if we just go back to VS Code for a second, we want to be able to adjust what's going on here inside the procedural macro output so that somehow we're getting that same result where using type inference, because that's all we've got here, we want to make the compiler decide which of these two, which function to call. And so I guess we're going to have to play around with this and see what works. And it's probably, I'm trying to think about this a little bit more, whether we can move more stuff onto the playground or we just start trying to add stuff to the procedural macro code. There's still quite a lot of complexity here. So maybe let's try and break it down in the playground a little bit more first and show why it's a little bit harder yet again in the procedural macro. Yeah, I think we'll do that. And then maybe from what we've figured out, we can go back to the procedural macro and get the implementation when we're happy. So the constraint for us is that we need to somehow get this to work, but we need the we have a form where the problem looks like this. We have some function, and we want to be able to call basically, it looks this way around instead. With the, okay, maybe let's line it up with what we had before. So we'll call this object length, and then let's have Let's make something that at least it looks vaguely like what we're doing on the PyO3 side, so that we can begin to recognize how this code might hang together. So we are going to have in here something like that, and we're going to be calling it like that, and then we're also going to accept this bound form. And we want to somehow get the deprecation warnings to fire on line 40, but not on line 43. Yep, we're going to need... That's not written right. There we are. That's good. It's giving me an error just because I don't need to name that type there, or that variable, and then we're getting the deprecation warning from before. We can not worry about that for now. Cool. So this code compiles and does nothing at the moment, and we want to somehow find a way to get the deprecation warning onto line 40. And it's a bit more tricky because unlike before, when we were able to just use this dereference trick here, we can't just do something like this here because that's not going to be a method on pyany. So we need to somehow come up with a different form of this. I think, well, first we can come up with a... We're going to need to wrap with some function. Let's call it extract GIL ref, just because when we want this to be the name of the deprecated function that eventually comes out in the compiler warning. And then let's just try having... What we'll do, we had our basic thing working, I'll remove that now, is we'll rename these to extract GIL ref. We probably don't need the prints anymore. And we're just going to, so the form that we had here, this extract GIL ref function, is taking in the argument, and we'll need to omit it again to forward it to object length. So I'm hoping that we might be able to do some sort of decision on whether to omit a deprecation warning based on that. And let's try a form like this and see what type inference does for us. I think that we might find it's more complicated. So we will just add a new method. And I'm going to replace requiring the actual type with requiring what Rust uses called phantom data. Sorry, I'm thinking a bit hard here as I type, so I'll try and explain how this is hanging together a bit more when I get to the end of this typing. Phantom data is used to just signify some type hint, t, without actually containing any data. So this is just a zero size nothing, but it's good for type hinting. It allows us to make these structures generic without doing anything. There is like implications for how these structures interact with lifetimes and subtyping and things, but I don't think it's going to be a problem here. So where have we gone wrong? Oh, we've forgotten our return type annotations. And I've written the wrong type name there. And those should be the values coming out, not the types. Yeah. So this is sort of what I feared might happen. Is that we've got some compiler warnings. So first off, it's good. Line 39 is giving us the result. Oh, sorry. Well, let's talk through. So I've changed our code around a little bit so that instead of A and B containing the value, we're still hoping to get that same trick. I've got A where I've given A generic type so that it can be associated with the type of the value, even if it's not doing anything with it. And the gotcha was that we were hoping to call the function extract GIL Ref and pass the value in and pass it back out unchanged, but use the same deref specialization trick to eliminate or deprecate only for types that have, let's call it is GIL Ref or something, because that's a bit more meaningful now. So we can mark it, and I guess we want to mark it for pyany. And then for bound, it's not deprecated, so we don't need to warn. Something like this. And then we can let type inference take over, which is what we kind of have to lean on in the procedural macro code. But, I haven't renamed it up above. Now, the problem, as we can see at the moment, is that 39 and 42 are both erroring or warning. And then we further get an error that this bound pyany here doesn't implement is GIL Ref. And that's because type inference is hurting us a bit still. We're having to rely on type inference because the procedural macro can't name any of the types. But we end up where both of these A new are deciding that T maybe has this trait bound. And then when it's seeing extract GIL Ref this way around, it's deciding that to call this method, that bound is needed. And so it's selecting this method always, and it's then having the problem that we can't actually use it here, and it's giving the deprecation both cases. So I wonder whether if we take the generic away from the structures, it might change things and make the functions generic instead. That's one route we could try, because that would change the way that type inference is working here. Or another trick might be to try using this value to do some more advanced type inference. Let's try making the structures non-generic. I'm not actually sure how this will pan out. So we'll give it a shot. We could just end up in a mess. So I will leave that constraint T here. I think the problem is that this will not be happy, and it might be where we get stuck. So I think the problem that we'll end up with having changed it to remove all the generics is that this T won't be able to be selected. So we'll have to move it here, where the problem is that the method's always picked up, and we've still got the bound. So I don't think we're going to do any better, but let's try and see what happens. Oh, we need to put a T on here. Yeah, so this is what I meant. The fact that the generic the type is introduced here, it's not constrained by the type A alone because A is no longer generic. But the problem is that by moving this type here, then we're going to get the problem where we always have this method selected. Because the difference between, we probably should have done that when we were explaining the autoderef specialization a little bit earlier. If it's up here, like this, on a type, then something like this method doesn't exist for T's that don't separate. This method doesn't exist for types T which don't satisfy the trait bound. It's just simply not noticed by the compiler. But this way round, this method always exists and the bound is necessary. So the fact that we've had to go to this to make the compiler happy is why it's then falling over down here. So we do need this type, the generic types all the way through, which is a little bit more annoying. I think what we can do though is we can go the other way. We can have we can attach the type hint more directly here. Like that. And that should force. The difference here is that when we weren't taking an argument and calling new, it's unconstrained, so the compiler can figure out whatever it likes to type. If we pass the argument in, we're forcing the compiler to fix the type based on what we sent in. So now we can do this. Where we've had to add this extra line in to solve the type. I think that doing it inline, let's try it inline down here. I think that this form will not succeed because there's the borrow on B here and we're moving B here. So I think we'll still get the compile error on the bottom line. Oh, okay, no, it works. Fine. So we might be able to do that. Great. And that looks like the result we want. So we have now, first we fix the type of our switch. Let's call it extractor this type. Just because that's a slightly better name for it than A, now that we're working with it. I think that's all of them. So we end up getting a deprecation warning only on this line now, where how this is working is that we first have to work out what we're getting, our desired value, and then we're using the type hint, or we're using this code here to work out what to do in terms of the type for extractor. And then that means that once we've solved that type, we end up with these extract GIL Ref tools working as we talked about before with the deref specialization, where the compiler can now reason about these types concretely, and we get the selected effect that we desire. So that's looking promising. So I think we can try and make that same thing happen in our procedural macro code. So it's going to end up looking something like where we currently have this. I guess we're going to want instead something like this as a warning. And so if we rewrote the code to the procedural macro code to work in that same way, I think we should end up with things working. Now, the one caveat, which is where we might fall over, and if we do, we're going to have to think about it a little bit harder, is that this expression here isn't a concrete type anymore. So over on our playground, we knew exactly what A was at this point here. But the difference here is that A, the type is still unsolved for extracted because we rely on type inference to work it out based on what function wants. And so the whole types all the way hang together on what we get out at the end. And that might be our undoing. If it is, then we'll have to go back to the drawing board and see if there's another way to achieve this. But maybe it won't work. But let's give this a shot and see what happens. So let's go over to some implementation code. And let's, in PyO3's impl submodule. So the impl submodule is a private submodule of PyO3, which produces code which you can reach from downstream crates, but it's not Semver guaranteed or anything. It's all hidden from documentation, and it only exists so that the procedural macros can reach into it. And let's paste in our types which we're doing this deref specialization with. We didn't quite get it all. We need this bit too. So that's now available for us to reach for from the procedural macros. And let's give this a bit of a shot. Yeah, if this so we haven't implemented his GIL Ref for anything yet. So we're more interested in whether we get any working compile at all. And then oh well, let's just do it quickly. It's this, isn't it? So that should be looking all the same as what we wrote in our playground. And the only question is now, if we change the procedural macro code, does it work? And that's the $1 million question in this context. So I think let's go find some of this code we're looking at. We're looking for, let's look for that function in our backend code. It's going to be here. So it's a little tricky because there's different forms of how the argument can be processed depending on whether it's required or whether you've put some particular annotations on it. I think in general that this all should come together. Yeah, here. So I'm going to just assume that we can wrap it here and see what we get. So we'll use this quote macro, which at this point, tokens is the procedural macro output. So it is new Rust source code that's going to be processed by the compiler later. And so we'll try taking that source code and we'll wrap it one more time. We want to get this form that we were hoping for. So I think it will look like this. And like this. And let's just try that and see whether this works. We might be at a dead end here, or we might have to start getting even more complicated, in which case I might want to give up anyway. It's not implemented for... okay, that's somewhat disappointing. So let's look at what the expanded code looks like. It's gone no. So we just failed to expand completely. I'm just reading this and having a bit of a think. So to reason about it, let's just go backward, or let's remove this bound for a second so that we get a compile just to check that things look like what we expect. So this is what we're trying to get. We're getting a deprecation warning firing. That's a bit. So we're hitting that top code path, but we're always hitting it, I think. Let's write both forms. Yeah. And let's expand again. So this is what we aimed for. We get the value, and then we've written the form that we found that worked before. And I think we're getting caught up in how type inferences are interacting with references, which is a little bit sort of frustrating, but not entirely unexpected. We've definitely got everything implemented correctly. Yeah, it's just forwarding the type. So this form hasn't worked for us because this type T, it looks like it's one too many steps for the compiler to, or it's clearly reasoning about things in a different way. I was hoping that this expression would be forced to be of the right type, but for some reason, I think maybe because the type is not absolutely fixed at this point, this reference is not behaving in the way I was expecting. Is it a typo? No. It's probably because no, I don't have a good answer for that. That's stretching the limits of my understanding of type inference. We'd have to go get a compiler expert to help. So we could give this another try by trying to put it into one more form. And if that doesn't work, we might have to call this one a bust. Unless anyone else has got any grand ideas on this. What we could try, which might work better, is, let's go back to the playground and sort of talk about a different form that might work. We might be able to implement it as a trait instead. So this is another form of the deref specialization. And we'll go like that. And then we make a generic implementation of it, which doesn't have, oh no, because the problem is here that I don't think you can deprecate trait. You can't deprecate trait calls in this way. So this isn't going to do what we want either. Sometimes we just hit the end of the road. I'm trying to think if there's any other way that we can do this that might be able to get the type inference we want out. We kind of need to... We could try just doing this. Guess. Like not wrapping it in a single expression. And that should help fix the type a bit more directly, right? So this form should still work. We'll have to change the way this works. We don't take the parameter anymore in here. And then we're hoping that the inference might then fix this more directly rather than having to go through the other expression, and it might solve our problem. I feel like probably the compiler will reason about it the same, but it's worth a shot because I'm otherwise a bit out of ideas. Yeah, so that has worked in our playground. Does that work in our compiled code? So this time we're going to take out the arguments here. We can add that back in for a moment. These don't have anything in them anymore. And, oh yeah, and then we need to change the way our procedural macro code is working so that we just add this extra line like we did in the playground. Right. This might be the final roll of the dice here. Either we get this to compile or we're in trouble. No. Let's think if we can get a little bit better. So we've still got the same problem where the type inference is not working in the way that we want. We're somehow, I don't know whether it's because the type is copy, we're getting that at this point, it's very generic. It's still very generic what's going on. Oh no, it's just not solved it at all. Type inference is not helping us. It's not to do with references. It's up here, isn't it? So there's clearly some interaction here, which is killing us. It's not able to fix this type. Yeah, that's the problem. It's not able to fix this type. And so then it's making a decision like we saw when we were playing around before, where the bound has to accept this and require this. So I think we might be at a dead end here because there's no way that we can sandwich. Oh, let's take the bound out again so that we don't set it. I'm trying to think if there's another way we can do this, where we can we have this code that's going to decide what type we need. And we need to somehow, once we've got this, try and emit a warning. I don't think we can. Can we turn it around? I think I've got one last idea. And I have no idea whether... I think we might end up with the same problem, where we're again going to fall foul of type inference. So there's one last trick we can play, where instead of going for this deref specialization, we can use the fact that methods are more tightly bound than traits. And what I mean by that is let's just simplify this down a bit more. So we'll have a generic type like this. We might not even... Oh yeah, we probably do. We'll just forward the type right through. And then we can also implement... We can create a trait which has the same function on it. And now, with both of those methods in play, we'll implement that trait for the type. Now we can have it written in this form. Missed a closing delimiter somewhere. Yeah. Oh. I deleted too much. Oh, that's not right. Yeah. And actually, okay, so that's now compiling. And let's try and make it match more concretely what we've got. Oh no, let's not go for that now. Let's talk through what we're doing here. So the thinking here, going for this form, is that we have two options available for this extract GIL Ref method now. We have the one which is on the type and the one which is on the trait. And they're both available because we've implemented the trait for the type. But because of the way the compiler reasons about things, it's always, oh, I think I know what the answer is going to be already. I don't think this is going to work. We might be at a bust, everybody. It could be that we've had a good run with procedural macros and trait fiddling around today, but we're not going to get there. And so normally the method on the type is always selected, not the method on the trait. If you've got this ambiguity here, that's how it gets resolved in the compiler. This type always gets selected. And I think I was going to claim that we could get the selective resolution here, but I don't think it's going to behave in the way we wanted. Yeah, it's going to error on every line because it wants this to be this bound to be satisfied. It's always selecting this method because we've named it like this. Try one last thing, which I'm pretty sure is not going to work as well. We will just try using dotted form. I'm pretty sure we'll end up with the same result. All right. Oh. Size bound is required just because we're taking self. So for the compiler to reason about the size of this self, we have to say that there is a sized bound there. I don't really want to talk about that more right now. Yet we still end up with the same problem where because the type's not fully solved, the compiler's leaning on this bound and picking this method. And then later it works out, yeah, that it needs to be of a different type. And it's not coming through, I think is what's going on. So we got very excited about how this could work, but I don't think we're going to have any success. So, and I can't think of any other ways to do this. So I think that's probably a good point to call that a dead end, unfortunately. So maybe just to wrap up the stream, might be worth, what I might do is switch over instead to a last piece that I was trying to solve for in preparation for a PyO3 0.20. I think it might be 3 patch release, and we can just get that piece finished off and push that. We can look a little bit at the way that the PyO3 GitHub Actions are set up. I think unfortunately, although we've tried very hard to make this kind of trick work to get a deprecation warning out, I can't see a way around the type inference problem where we end up being able to convince the compiler what this is solidly so that we can then have that solved correctly in the way that we were seeing the deref specialization. I think we've got too much type inference going on here, and it's causing the compiler to get excited and select the problematic option always, and with the trait bound, rather than giving that smart switching that we saw before. If we could somehow figure out a way later, maybe I'll have an idea off stream later, to reformulate this so that the type is fixed. Oh, maybe I've got one last idea. Thinking about it. What we could try is making this extractor own the value temporarily and then release it again, and that would force the type. Let's give that a shot. It would be cool to solve this if we can. So sorry everybody for seeing like 15 different ways how not to write your very, very mad tangle of traits today. What we're going to do one last time, we're going to make the type actually own the value. And we're going to go back towards more what we had before with two types. And do that kind of specialization. And then I think this is still going to fail. I think we're going to have the same type inference problem. Oh well, we're going down this road now anyway. Sorry, everybody. So we'll have we'll build it, and then what I was going to do is instead, let me think about this. We're going to need to we'll keep this where it doesn't do anything. It just does that. And then we're going to add one last method, which is going to have, we're going to unwrap this again to get back the original T. And what I thought might happen by doing this is that we could fix type inference a bit more like this. But I think we're going to end up with exactly the same problem where at this point, this is still not totally solved. And so we end up getting a bit stuck. By the same problem. Oh, need this. So we'll shove the value into this extractor type, and then we'll take it up again, out again. Oh no, we need to do this time. And this would be the point where we hope to create the deprecation warning. And this is going to work very nicely in our playground again, where types are solved. Oh, this trait we don't use anymore. What have we done wrong? Oh, we need our derefs back again. And we want to deprecate this one. I think this is going to fall out with the same conclusion. Sorry, I'm just getting a bit lost in thought there. I should try and explain where I'm going. I'm just sort of trying to think ahead already to if there's any other way we can achieve this. I might have one last even madder idea if this one doesn't work. Okay, so where are we at? Oh, we need this one as well. And then we should be at the point where things hang together. We need the trait implementation. Yeah, we get the warning of the deprecation. We forgot to do this. Yeah, so we're back to a form that works, but I still think that we're going to have the type inference problem here. We'll give it one last shot, and then maybe we can even go a bit wilder. I'm wondering whether we can get this to a point where we can turn things around so that the type T is fixed before we make this call to this extract GIL Ref helper. I think I have a thought. I had a thought just now, but we'll try this form first, and we're slowly going to get more and more wild, and then we'll see whether we can get the last thought to work as well. If it may not, or it might, but we'll see. Okay, so how do we need to change this code? We're still very similar. Oh, we can actually just copy it in now, can't we? Because we've written it in the same way. I think we're still going to have a compile error from this. So this time we do that. Oops, no, that's not what we want. We want to save that. We want to try and compile. And oh, we forgot to add up onto all of these. Okay. Yeah, we're in exactly the same problem. I'm going to try one last crazy idea. I think this is going to be a bit harder to achieve, but I think what I'd like to do is what I'm going to try and do is end up with, I don't want to do references. I want to try and fix the type T all the way through. And I want to try and get to a point where we end up calling this extract GIL Ref helper later on. And we're going to have to dance around a lot with the procedural macro to achieve that. Let's just look how it might look. If this doesn't work, then I really am bust. We're going to add one more trait. We're in one more type. And the idea here, this is really pushing the limits. If this works, then I will be really pleased. it could be that it's still hard to figure out what's going on or the inference still works against us. But it might be that we can delay. We might be able to delay the call by what I'm thinking long enough that the compiler gets a chance to fix the types in the way we need. So what we're going to do is we're going to just have this method, generic thing that takes the argument in and returns a tuple of the type and the this extractor. Might give it a better name in a sec. And so we'll return both out. So we can do that. We're going to remove the parameter again. Use phantom data here. Okay. And so now what we can do is we'll end up with a form like this, where we've created that that hint, but we can then turn it around this way. So we just passed A, if you like. We can call it A again. We've passed A through this method just to sort of pick up the same type, but we didn't do any references or anything anywhere, which I think means that this type will be concretely held through as far as type inference goes. And then we'll want to do this afterwards. And it's going to get a little bit awkward only because of how the procedural macro is set up. But if this works, it's going to be quite amazing. Maybe we can try and reason about it in this playground, if it will, rather than try and implement it in the code, in the real code, because it's going to be very fiddly to move the procedural macro around. I'll show you why if this compiles. Great, so we get the same result still. And so why is it hard in the procedural macro to do this? Because, we'll have to take this bound away to get the compile to be happy. Now, to achieve this same effect here, I think what we're going to have to do is we're going to have to because we got them inside the expression position here, we need the last statement to just be the value. So we end up back at the problem where we've got things the wrong way around for what we think type inference might work like. I mean, this may still not work when we go into the full type inference situation. But so what we need to do is somehow maybe achieve something like this, where we save it and it will look like this with our inspect type function. And then we save that, and then we return that. And I think, hopefully, by doing that, we fix the type here. I don't know what the order that type inference is going to play, like whether the compiler still won't decide it. And then we'd need to do something like where we save the result. Then make our call to decide about the deprecation, and then finally return the result. And what I'm not entirely sure, we'll try and see if we can push the compiler to its limits here. is whether by writing it this way around, the compiler's forced to make a decision, or at this point it still doesn't know this type, and it's forced to make a decision about it here because of this point here where it's being used in the code inside the function call. And then finally, because it's been forced to decide on the type, this might work, is what I'm hoping. It's a bit spaghetti. Let's see if we can replicate this same situation in the playground. So how are we going to do this? What we'll do... we can just... we'll have a... what we could do is we could derive default like this for these types. That should just be fine. Yeah. And then no, that's not going to be good enough. No, what we're going to do, we're just going to try and play with the type system by having a... So we'll go for, what's the function called over in our code? It's called extract argument. Let's try and like get to a point where we're thinking about where the playground looks a bit more like that. So we'll create a function extract argument. We'll just give this a to-do. And we will introduce a type. We'll just do like that. So we're trying to like get type inference to work in the same way in the playground to at least prove whether this is possible before we pick the procedural macro apart. So we've got this function which is trying to work out a type based on what it's doing. And we don't need to have anything in here. And we can implement extractable for the pyany. And we can implement it for the bound pyany2. And now we're going to take these hints away and try and let type inference start running. We're not going to get anywhere yet, because now there's nothing to fix any types, and so the compiler's going to have a meltdown, I think. Oh, there's no lifetime here, that's right. In this form. And it's type annotations. It can't solve anything, which is fine. And we could try to fix that by creating two functions here which are concrete instead. So let's take the function which takes any, and then we've got the bound form. And so this is looking a lot more like what we've got going in the real code, where we somehow are producing something, we're calling the inspect type on it, we're then calling a concrete function where we know the type, we're forcing the type at this point, and then we're calling with this extractor, which had an inferred type, but should now be fixed from here to run that. On the use variable, that's fine, we can remove those. I think it looks like it might have worked. That's looking incredibly promising. We've gone round got absolutely around the houses, but I think here we have something where it actually is doing what we want. We've got type inference carrying it through all the way, so that we eventually, when we do call this point, we know that the type has been fixed. And so we're ending out, I think we're going to be able to make this one hang together. We're getting just the one deprecation warning on this line 60. So, wow, this has been a bit of a meal. I'm sorry for all you viewers who have just seen me like flail with trying to put this design together for 45 minutes. I tried to express the warning that I didn't know whether this was going to work when I sent the announcement out for this stream. And I think it looks like this might work. We're really close to the end of the time that I had available today. So we'll try and continue on the procedural macro just a little bit. Let's see if we can hack something together in 10 minutes that gives us a final answer. And otherwise, we're probably at the point of wrapping up the stream. So it'd be very cool to see if we can get this to work. I'm going to do something really crufty and just add code wherever I possibly can to try and achieve the result we want. Okay, so okay, I'm just going to dodge it like this. We wanted to have this extractor stored under the holder. So we're going to have to do that. And then, okay. Gonna have to just feed this all through a bit. I'm trying to set this up in the procedural macro so that we get that. We looked at putting the extractor up here and then doing some code down there. So let's first try and see if we can plumb that assignment at least, which is all a bit brutally hung together at the moment. And so now we can have this form, which is what we talked about. Let's try it like this. Oh. This is gonna probably break stuff, but okay. That might break other code, but we'll worry about that another time. I'm just trying to bodge something together in our procedural macro to look like what we wanted. Let's save this as our target code for a sec and do the... Oh, something's not worked there. Found keyword use. How have we managed to achieve that? Oh, we put a use there. Yep, that's no good. Yep, so that's fine. No, we still need to define the function first. Sorry. All good. Just had someone arriving home. We need to add this extract type in here. So let's add those in. Okay. We don't need this method anymore. That's fine. They're not used. Oh, we need this. Great. And now if we compile, so what we've now ended up with is that we are doing the type inspection. We're saving this value, extract to 0, but we're not actually doing anything with it yet, which is fine. And so we just need to do some extracting. Let's really bodge this for the moment. I'm just going to find somewhere in the code where we do this. And I just want to transform this code into what our target code was, that we're going to save the result, and then we're going to call this extract GIL Ref method on the extractor, and then just pass the result back out. And let's just finish up. I'm just going to do a really crude hack to try and get the expanded result by adding it onto this same code here. So we can do this, and then this is definitely not right? Because I'm just calling this method. I'm hard coding it for one value. There's loads of things wrong with trying to put this code here, but I think for the sake of answering whether this whole thing is going to hang together, this is a good point to put this code. I'll push it after the stream if this works. And then there'll obviously be some tidy up to do. So let's compile this. Cannot find extractor 0 in the scope. Okay. That's fine. That's because probably the hygiene that we gave to the symbol. We can talk about procedural macro hygiene. We might continue tidying this code up next week, to be honest. If we get it there, it would be cool to see it finished. We can talk about the macro hygiene then. Yeah, we'll just give this a different hygiene. The macro hygiene is trying to defend you against using identifiers that you shouldn't be able to access. We can talk more about that next week, perhaps. Let's try compiling again. No, it still didn't hang together. Do we get any expanded result? No. That's a little bit frustrating. Let's see if this worked as we expected. That's the target. This is what we got. So we are using that. Have I just used the symbol wrong? Well, let's try and force the hygiene here in the same way for the moment. If not, we'll have to try and plumb this through a bit more properly to make it the same ident. So that's the symbol that we're hard coding. There we go. Let's see whether that works from a hygiene angle. Still doesn't work. Huh. I haven't typoed it, have I? No. That looks like the same result, but for some reason hygiene isn't liking it. Have we got any other hygienes that we can call? I would have thought that the call site hygiene would work there because it should be the same. I am a little bit puzzled why that's not worked. Okay, we'll give it one last shot. This will be a bit more correct anyway. Let's pass the extractor back out. And then we might be able to pass it into the right place. It's going to get very messy. We're going to have compile errors left, right, and center, but it'd be really nice to answer whether this works. So we're just fixing type annotations from all of the stuff that we've broken. We're going to have to fix the macro somewhere else. Here we need to clone this value now. Yeah. What line is this here? Okay. Probably more practical. It looks like this has been plumbed through a lot, so maybe we can just find and replace here. Right, just swap all those. Maybe we get closer to a compile. And then this is now, yeah. Because we started stuffing other stuff in the in that vector, we're having to just pull out the first items for these places. This is all really bodged the code. That's fine. There's a lot of refactoring that could do if we get to it. Oh, it would be very nice to answer whether it works though. Clearly, I'm breaking code left, right, and center here. That's fine for the moment. Just pulling stuff around. I don't really want to talk about the code that we're changing in any great detail, and so this is probably where we're, I don't know. So there's going to be loads of code that's going to be all broken from this. And there's a lot of it, which is why I wanted to do it in the playground first, because it seemed reasonable to try. Yeah, because I've really just abused a variable that I shouldn't have, which is why we're having to add all these fixes back in. So that might now compile. Yeah, but we still just need to find that extractor 0 value and plumb it through properly. And I really hope that this works, because it should then be exactly the same symbol. If it doesn't, then I'm a bit puzzled. So we forced it onto there, into that holders variable. And so now we can actually get the extractors properly, at least. And we can use those. Oh, I'm going to need to remember. I think it's like that, the syntax that we want. The quote. There we go. So now we just need to find uses of this and fix it. Let this work, please. Well, something didn't work. It might be hard to figure out what. Let's see whether we got a successful expansion there. No, we didn't. Oh dear. Cannot find value extractor in this scope. Oh dear. That's because we hard-coded extractor in some places. This will probably fix it. We still had a failed compile. Problem is that it's inside PyO3's own code base, so that's why we're not getting the successful expansion downstream. Oops. I'm just going to close the door, having just had someone arrive. This is the target one that we want. So we're calling it always for this. So extractors, we must be doing the wrong thing. One of the places where we just shoved things in must have been... oh yeah, here we are. We did the wrong thing. So now we've wired that through. I think it's still not very clean. Cannot find extractor 1. Oh, so that's probably related to this bit. No, hang on. I think it's this one. Let's do it like this. We'll make it optional, and then because I think we've just created an ordering problem somewhere, so I think by doing this we might get there. We're still having a problem. Where is it going? It's in the same place. Problem that we're having is that because we've got macro code inside PyO3 itself, we're struggling to compile. Maybe we can just comment that out for now. Maybe that's a smarter idea, and then we'll work out what's going on later. Should be broadly okay. Maybe that will compile. No. I should have thought we might have to think about this later. We can comment out that. Maybe now, just having got rid of all that problematic code. Okay. We got somewhere. Let's force it to think about that. Did that disrupt the stream? I think our expanded code finally looks in the form we want. Yeah, okay. Oh, that's what we did wrong. We changed the generated code as well. We can take that wrapping away. And there's a lot of warnings, but we finally get the form we want. And I think if we now just check, I think we haven't put, we did put a deprecation warning on there, but we didn't put the bound. Deprecation warning didn't fire though, did it? Maybe it will in a sec. No, we didn't get any deprecation warning. That's incredibly disappointing. I think, everybody, that this has run a good course. I'm not quite sure where the state of the code is. I think I'm going to have to go tidy this off, but my family is now home. So I'm going to have to wrap up there, I think, and go help them get set up for the rest of the day. We got the code into the form we thought, where we thought that this would be able to at least have the output that we desire and give us the deprecation warning. But for some reason, we're not seeing that deprecation warning come through, even though I think we've got it planted nicely here. Oh, maybe the last step is that we just need to try that one last go. Aha! There we are.
I just missed out the one final trait implementation. There you go. I know it's been a bit of a weave through maybe the last hour of trait madness, but we have actually got to a result. It's not in the right place. It'd be nice to get this argument on the actual code itself, on the argument rather than just on the pyfunction attribute. Like if I go back to the source code, where I would like it to be, you can see the deprecation warnings being added here, but we'd like it to be added there. So wow, we've gone through an absolute whirlwind in that last hour, and I probably would have liked to explain what I was doing in a bit more detail, but I was also just deep in trying to figure out if that actually could work. And wow, the number of iterations that we went through trying to hook this together. Thank you all for your patience in just observing me try different things until eventually we got to this form where the type inference fixed the value type early enough that then when we called this, we could rely on the deref specialization, which we talked about. I think I will have a look at what the code got to off stream and decide whether it's in such a wild space of mess that it's better for me to just clean it up off stream, or whether there is actually something interesting to talk about in cleaning it up on stream next week. Otherwise, I haven't really strictly decided what to talk about. So I'll have a little think about that too, and then send a stream announcement round probably middle of next week again, once I've figured out exactly whether the timing works still and whether and what I'd like to talk about. But yeah, okay, cool. So we did actually prove it works, and I'll go push this code in a sec, but we've got quite a bit to do before this code gets merged. Thanks very much, everybody. I hope you're all well, and I'll see you next week.